Hi, this is Fatima Isaac and I'm presenting the final presentation of S2P2 for Senior Design 2. The group comprises of me, Kana Pulliam, and David Rivera, and our advisor is Dr. Hussein Salifur. And this project is about building the Bluetooth tether device. It's hard to imagine our life without use of a cell phone. It has our contacts, our emails, our pictures, our videos, and even our bank accounts. They're also used to locate the location in case someone is lost or needs directions. Americans lose a worth of $30 billion of phones every single year. In order to see if we were the only ones who left our phone somewhere and forgot our keys, we conducted a survey, and as expected, everyone once in a while loses their phones, keys, mobiles, tablets, and iPads. Isn't it so frustrating? These are a few available resources in the market, but they aid only in recovery. It's better to prevent rather than waste your time and energy on the recovery. Our goal is to develop a low energy and low cost wearable item that can be a watch, which will alert the user if it's 10 to 15 feet away from the cell phone, either by buzzing an alarm or illuminating the LED. And this will be done by using the tethering technology. Tethering is a wireless connection between two devices. In order to alert the user, we decided to use the Bluetooth technology to tether a cell phone to the Arduino microprocessor. The Bluetooth low energy radio frequency device will form a connection between the Bluetooth enabled smartphone and the Arduino microprocessor. So this way it will tell the user that the phone is now out of range when it goes beyond 10 to 15 feet, either by turning on the LED or using the beeper to buzz. This is just a pictorial depiction of what I have just said. This is a person having the Bluetooth watch or any wearable device, and when the distance is about 18 to 25 feet from the cell phone, it's going to alert the user. The Bluetooth app is free to download from the App Store, and this was used for establishing the communication between the cell phone and the Arduino. And it has two selections for communication, but we'll be using the Monitor UART. This is a list of hardware components we used for the initial circuitry, and when the circuit was miniaturized, some extra components were also used, and they'll be shown later in the slides. But the Bluetooth LED, speaker, buzzer, and the breadboard will remain the same. This is the picture of an Arduino Uno board, and it has the microprocessor right here. It has 14 digital pins and 6 analog pins. Operating voltage is between 5 to 7 volts, and the microprocessor will be programmed using a combination of C and C++ language, and it's the Adafruit software. This is the Bluetooth LE device, and it's responsible for establishing the connection between our wearable device and the cell phone. It works by stimulating a UART device beneath the surface and is responsible for sending the data back and forth between the two devices. This picture shows how the circuit is composed of the Uno board, the buzzer, and the LED with the resistor. The resistor is almost 150. The piezo buzzer has a frequency of around 800 Hz. This is a system decomposition diagram where you can see this is the cell phone, which is connected through the Bluetooth technology to the Arduino microcontroller. The microcontroller needs a battery to run, and this will alert the user either by the audio speakers, like in the form of a buzzing sound, or alert the user by illuminating the LEDs. This is our first working circuitry. You can see the Bluetooth LE device right here, the Uno board right here, the piezo buzzer of 800 Hz is right here, the resistance of 150 ohms is here, and here is the LED. This slide shows the hardware interface between the LE device and the Uno board. A few pins I can tell you about is the MISO data pin on Bluetooth LE is connected to pin 12 on the Uno board, and the data is sent from the module to this pin. The SPI data pin is connected to pin 11 on the Uno board, and the V-in, which is 5 volt, is also connected to the Uno board, and the ground of both the devices is also connected. The Adafruit software is used for this, which will establish the protocol reactions when the Bluetooth LE loses the communication with the cell phone. And the LED and piezo buzzer are not in a parallel circuit. They are designed to be independent alarms. Just in case if one fails, the other one is there to alert the user. And this flowchart shows how the software is going to work. In case of a mobile phone detection, the LE device will detect it first, and if it does, it sends the signals to the microcontroller, and when the microcontroller feels that the distance is increasing from the user, it's going to alert the user by beeping the buzzer or illuminating the LEDs. Initially, we thought of a prototype to be a wearable device like a watch or a bracelet, but the high cost of PCB design and a lot of time needed to make it, we decided to change it into a clip-on device, which will be shown later. This slide shows the individual tasks by each member. The circuit design for hardware was completed by Fatima, and software was done by David, and the prototype design was done by Kana. There were many problems in our initial circuitry. We couldn't change the output transmission power that was set by default. The pins were not working as expected, the circuit LED wasn't bright enough, and the first code for the software was not at all successful. Miniaturizing had some own problems. It came with a high price tag, and we also needed a battery that shouldn't run out so quickly, and the distance was a main thing. We aimed to make the device work at almost 15 feet, but with the original circuit we were going up to 45 feet. In the first picture of the circuitry, I showed a speaker of 8 ohms attached to the breadboard, and it was not working the way we wanted it to work, so we replaced it with the piezo buzzer. The biggest advantage was that it's 1:20 ratio in size. So the original LED was also replaced with the LED at 2.5 volts, and it was now working with sufficient brightness. A new code for the software was generated, and it was successful enough to establish the connection between the microcontroller and the external LED, but it did not have any impact on the distance. So as I've already told about the miniaturizing high cost and the time limitations we had, we changed the prototype design from a watch to a clip-on device, and for the distance problem, we tried to modify the antenna design for Bluetooth LE, but this did not work well, and finally we got to use the RF or EMI absorber foams. They were put into the circuit. It's a black colored foam, and it was used to control and reduce the transmission power of the Bluetooth LE device. That fortunately worked very successfully, and we were able to reduce the distance from 45 feet to up till 18-20 feet. The final goal was to miniaturize the circuit with supporting software, and to do this we had to replace the Arduino Uno with the Pro Trinket. It's very small, and you will see it in the pictures in upcoming slides, and a small clip-on device that was easy to carry, easy to attach to your belt or your purse, or just put it in your pocket was also designed. This slide shows the lithium battery, the battery backpack, the Bluetooth LE, and the Pro Trinket right here. The resistor of 220 ohms is connected via the LED. The LED is 2.8 volts, and it's red in color. The piezo buzzer and LEDs are on a separate system, a redundant alarm indicator. This is the whole circuit for the miniaturized part of the project. You can see the Bluetooth LE is right here, and the Pro Trinket is right here. This is one LED right here, and the resistor is here. This is piezo buzzer. This is a lithium battery source, and it is connected to a battery backpack to provide the power. Here are 2 more LEDs, and see, this circuit is a bit different from the first one because of the extra components. Here on the left hand side, you can see in the picture the difference between the Uno circuit board and the Pro Trinket. See, it's so small that we decided to use this one for the miniaturizing of the circuit. And the picture on the right hand side shows this one is the original circuit we made, and on the extreme right hand side, this is the miniaturized circuit. From the picture you can see that it's taken when it was simulated. These are the results of the test we performed on the initial prototype, and the data is distribution is normal, as you can see in the graph, because it has a normal p-value of 0.343, which is exceeding the value of 0.05, indicating a normal distribution. The summary report and performance repeatability factor is also greater than an index value of 1, boosting 95% confidence interval for world-class performance within established tolerance of 40 to 50 feet. This slide shows the test results of the data which was performed after the RF shielding, the EMI absorber foam was introduced in the circuit. The data distribution is also normal here because it has a p-value of 0.358, exceeds the index value of 0.05, indicating a normal distribution. The PPK is also greater than the index value of 1. It also boosts the 95% confidence interval for world-class performance within established tolerance range of 15 to 25 feet, which was the initial goal of this whole project. Some information we needed for the testing of the circuit was provided by Adafruit verbally. So this is the picture of the prototype. The one on the left, this one, is the one we initially planned to make. But you know, sometime unforeseen things happen, and unfortunately this fried up. So we changed almost last minute to this prototype, and it's contained in a plastic box with a clip-on device attached to it. It's a working prototype, and you will see this in the simulation videos. With the clip-on device, you can either attach it to your belt, to the purse, or simply just put in your pocket. We did think about the future of the product with the marketing and all that, but the 3M company who provided us with the RF shields and the foams and the kit for the design, they restricted our prototype only for to be used at the university projects and not for sale. And it's totally uneconomical for us right now to market this product. Here is the price list of all the components that were used in the project, the miniaturizing and the original both, and the prices are written with the sources. All three of us have worked very hard, and we put our best efforts towards this project and approximately spent 12 hours per week, and we also communicated through text messaging, conference calls and emails regularly to help each other with the project tasks. And the Gantt chart shows the tasks performed by each member in the project and the time limitations. You can see the projects and the time limit within which each task was completed. This timetable is just added as an extra because the font in the Gantt chart was a bit small. So these are the tasks that we performed within these time duration. This is the last slide of the project, and it has the links to the YouTube videos we posted under the Senior Design account for the simulation of the project. We all are so happy to see our project working, and that's all for now. Thank you.